sun is our star.
Our life is dominated by the sun.
It's relevant for human history, for human culture.
It's been observed by humanity since a long time ago.
Everything that happens on the sun produces repercussions for us.
We live in the sun atmosphere.
The sun is our Rosetta Stone to understand the rest of the stars.
To understand this star is crucial.
But the sun is a very complicated laboratory.
There are a number of really important questions that are open in solar physics.
And it's still not fully understood by us.
It's mandatory to continue to observe the sun.
The European Solar Telescope is our next step in the study of the sun.
We'll have a 4-meter aperture.
And the efficiency of instrumentation.
Going to zoom into the sun.
Technical challenges will be a lot.
Because we never had such large telescope.
Not just for a bunch of solar physicists, for the whole mankind.
A large telescope like the European Solar Telescope will change what we know about the sun.
The sun. Throughout history, our star has been observed, studied, and monitored. From cities, mountains, islands, the sky, and even from space. But our story began here in Italy, more than 400 years ago. In 1610, the Italian astronomer Galileo Galilei observes the sun daily through a telescope he made himself. He draws and writes down everything he sees, especially those mysterious and disconcerting sunspots. It is the beginning of solar science and the fall of a god.
We start solar physics and science with the sun, and in this library we have the first book of Galileo Galilei about the observation and the demonstration that the sunspots are really on the surface of the sun. With the use of the telescope, Galileo demonstrated the sun is not perfect. The sun presents spots.
The maculated sun, it's dirty. There's things that you would like to wipe off.
Most likely, when observing the sun, Galileo was not aware of the origin of sunspots, but he was able to understand that sunspots are a solar phenomenon.
A solar phenomenon that started a whole revolution, not only in science.
If you look very far back in time, the sun was a god. Because the gods were important, the gods determined our lives. In the heavenly spheres, that means it was a perfect body. But then when the telescope was invented, soon after that, various people all over Europe saw that the sun was not perfect. There were spots on it. And this was a revolution.
Galileo observation has been the most important for a couple of reasons. The introduction of the instruments to improve our sense.
But above all, the genius from Pisa transformed the sun into an astrophysical object. Today, it is not necessary to draw sunspots on paper any longer.
Well, observation of the sun has changed over the last 4 centuries.
Galileo only saw basically dark spots on the sun. What we can see is the tiny structure.
Sunspots are dark spots on the solar surface.
Very similar to pimples on human face.
From 10 to say 16 megameter.
Apart from the dark thing in the center, which we call umbra, we have a filamentary structure around it, which we call penumbra.
The intensity is decreased in sunspot umbra compared to penumbra, and in penumbra compared to quiet sun.
Sunspot is dark, so it will be very cool.
4,000 degrees, which is a lot cooler than in the surrounding quiet sun atmosphere, which is about 6,000 degrees.
If you take out the sunspot and put it somewhere in the sky, it will actually glow.
To understand these incredible features, it was necessary to build larger and larger telescopes, capable of observing the sun in more detail, with greater resolution.
The resolution, how small the structures are that we can resolve on the sun, depends on the size of the telescope.
The larger the aperture, the smaller are the structures that you can resolve on the sun.
So right now Gregor can do 50 kilometers in the blue, and we can of course get much further with EST.
Well, with a 4-meter telescope, we expect to observe details as small as 20-30 kilometers on the solar surface, which is factor of 3-4 much better than what we can do with our 1-meter telescopes that are operating these days.
So it is a big step forward in our ability to observe the sun.
But Galileo not only had a telescope, he also had a method.
Galileo made observations each day at almost the same time. This allowed him to recognize the solar rotation.
The sun rotates faster at the equator than it rotates at the poles. The reason why this is so is still not understood.
And not just rotation. More than 400 years of systematic solar observations have revealed a periodic star.
And then another huge milestone was the discovery of the solar cycle, that the number of sunspots goes up and down with around 11 years.
During which the phase of the sun, the surface of the sun, changes its aspect following a cycle.
A general open question is, why does the sun vary in an 11-year cycle?
Galileo's telescope opened up a new universe of questions. What are sunspots? What is the origin of the solar cycle? What is the sun made of? Each observation, each drawing, each page was an unanswered question.
When Galileo observed the sunspot in the sun, he started to understand that the universe is really complex.
With Galileo, we discovered the complexity of the sun, but we still did not know how to understand it, until a Bavarian lens maker and a French eclipse hunter came up with new ideas. In 1814, Joseph von Fraunhofer dispersed sunlight with an instrument he had invented, the spectroscope. He observed some dark lines on the solar spectrum, the unmistakable fingerprints of the different chemical elements present in the sun. Then in 1868, during a total solar eclipse in Guntur, India, a French astronomer used a spectrograph to observe a bright yellow spectral line that did not correspond to any known chemical element on Earth. A few years later, the new element was named helium. In 1876, he established the first professional solar observatory in Meudon, France. His name was Jules Janssen.
When Jules Janssen look with spectrograph, he is more focused on the physics, astrophysics and solar physics.
Spectroscopy is one of the most important analytical tools that we have in order to understand anything that's out there where we can't get there directly.
Look at spectra, you don't have your typical image of the sun. So typically you have a slit, light enters through the slit, and then the light that goes through the slit is dispersed in wavelengths.
We see signatures of chemical elements, we can measure viscosities, we can measure magnetic fields.
Thanks to those lines hiding in sunlight, we learned, among other things, what our star is made of.
99% made up of hydrogen and some percent of helium. There are also other elements which we call a metallic element, but they are not metal, they are also present on the sun.
When we look at different wavelengths, we look at the element in different state, and so different temperature, density of the plasma.
When you are looking at different spectral lines, actually you are trying to look at the various layers in solar atmosphere.
150 million kilometers away, on a blue planet more than 1 million times smaller, the combination of technology and ingenuity has allowed us to access the interior of the sun. Like a bird discovering the Earth's greatest secrets from above, only at an incredible distance.
The sun is a sphere made of plasma.
It is made up of mixture of electrons and charged ions, so this is the plasma.
The sun has basically 3 main zones. The core of the sun is where nuclear reactions happen and energy is released.
Produces a lot of energy by burning hydrogen.
This fusion reaction creates photon, which actually travels from core to the radiation zone.
The radiation basically carries the energy.
And then you have convection zone.
So convection brings the energy up to close to the surface.
The visible layer of the sun, which is photosphere.
The photosphere, the surface of the sun, spotted and bubbling. This is where granulation occurs.
So granulation is the manifestation of convection on the solar surface.
Hot gas is rising, cool gas is going down.
Transporting energy from the deep layers of the atmosphere up to the upper layers, releasing the energy there and then going down again.
The solar granulation pattern is fundamental to everything that is happening on the surface.
But the sun's atmosphere does not end here. Above the photosphere, there are 2 more layers exceedingly difficult to observe: the chromosphere and the corona.
And when you move further in the height, you come to another layer, is chromosphere, which is the very famous layer which is usually seen during the eclipse, because you see these bright filamentary structure which are prominences. Much further, you encounter another outer layer of sun, which is called corona.
It's 1,000,000 times less bright than the solar surface, than the solar disk.
But it is actually at very high temperature.
You have to think that when I go from the core of the sun to the outermost part, the density drops by 30 orders of magnitude. So we are dealing with totally different regimes.
Something that early observers soon discovered is that the solar atmosphere is full of changing, enigmatic, even violent phenomena, like a strange and erratic forest of fire.
On the solar surface, we observe many different structures having sizes from 100 kilometers up to 30,000 kilometers.
It's covered with all kinds of structures which are changing all the time.
Prominences and filaments, which are much larger than sunspots.
A whole range of explosive and eruptive phenomena.
The sun is constantly changing. The sun is never the same.
In fact, in the atmosphere, it's completely inhomogeneous. So you have to think about the sun like a volume, like a 3D. All what happened on the sun is in 3D.
They start from the surface and follow the process, how the energy is moving or the heat is moving, or from photosphere, chromosphere into corona.
But the sun is more than just a succession of overlapping layers. They are all intimately connected. Understanding how they are related is crucial to understanding the sun.
EST is mainly intended to study the coupling of the different layers of the solar atmosphere.
It also includes a very comprehensive set of instrumentation covering the whole visible spectral range and the near-infrared spectral range.
To understand how these phenomena originate and take place.
Sunspots, prominences, spicules, loops have been observed for centuries. What is the origin of such a varied zoo? Is there a common cause behind all this diversity? Part of the answer came in the early 20th century from across the ocean, and it couldn't have been more surprising. In 1908, the American astronomer George Ellery Hale observed the sun with a large spectrograph he had just designed and built. He discovered that the lines of the solar spectrum were split in sunspots. This is the so-called Zeeman effect, proof that there are strong magnetic fields on the sun. His discovery changed our perception of the sun forever.
This was the first time that a magnetic field had been seen away from the Earth. And now we know in the meantime that this magnetic field is responsible for all the dynamics, all the huge amount of activity that the sun shows.
From very tiny scales, very small features to large.
The impact of the sun over the heliosphere, so the huge area where the planetary system exists.
The main discovery, because it told us the sun is not just some random ball, it's actually a magnetic star.
Yes, sun is a big magnet. It's a magnetic star and it's a big magnet.
From among the trees of the German city of Potsdam, an architect's dream arises. In 1924, the expressionist architect Erich Mendelsohn unveiled his masterpiece. It is not an auditorium or a theatre. It is the Einstein Tower, a solar observatory designed to demonstrate Einstein's theory of relativity. While it failed in this task, it still provides beautiful and mesmerizing views of the sun.
Hale used actually a very similar telescope as the Einstein Tower, so also a celostat system to collect the light, and also he used a spectrograph, but in addition to that he used a polarimeter.
So when you look at a spectral line, usually you have just a spectral line like this on a spectrograph, but with a magnetic field it starts to broaden and split. So what you will see is the broader the line and the more components you see, the bigger the magnetic field.
But this can only reveal the intensity of the solar magnetic field, not its direction. To do that, we have to measure the polarization of sunlight.
Polarization is an intrinsic property of the light.
If there's a magnetic field present on the sun, then the polarization of the light that we receive from the sun here on Earth will changing.
So to study the direction of the magnetic field, we need spectropolarimetry.
To see spectral lines in different polarization states.
You get a three-dimensional vector, so you know also the azimuth and the inclination angle of the magnetic field.
We need a telescope which can give you all the directions of the polarization of light, and we need to interpret that correctly to get the three-dimensional magnetic field.
That actually turns out to be an incredibly difficult thing.
Drawings, pictures, observations at different frequencies. These were useful, but to obtain a complete picture of the invisible solar magnetic field required spectropolarimetry.
So the first thing that strikes you when you compare the sun's magnetic field with that of the Earth is how much more complex it is.
Actually, The main manifestation of magnetic fields on the Sun had already been discovered 3 centuries earlier. Galileo was right. Sunspots are intrinsic to the Sun and the most obvious proof of its magnetism, although that he did not know.
A sunspot is a huge concentration of magnetic field.
Actually 4,000 to 5,000 higher than Earth's magnetic field.
We know why they are darker than the surrounding. That is because the magnetic field which is there makes the convection, the energy transport to the surface, much less efficient.
So the umbra, the middle part of the sunspot, the magnetic field is coming out of the sun, vertically more or less. And in the penumbra, the outer part of the sunspot, it's more horizontal.
And it's a very unique feature because then the strong magnetic field is interacting with the surrounding plasma.
All this together makes sunspots a very complex and interesting phenomena to study.
Not the result of meteor impacts, volcanoes, or shadows from unknown planets. Sunspots are caused by giant magnetic tubes. But where do they come from? How are they formed? How are they maintained?
How that magnetic field is generated, first of all, that is a question.
Well, the current thinking is that the magnetic field on the Sun is produced deep inside the Sun by a so-called dynamo process.
Plasma is made up of electrons and ions, and when the electron and ions move, it creates magnetic field.
There are strong concentrations of magnetic elements formed inside due to the rotation of plasma.
It's like a flux tube.
The magnetic flux tubes are rising on the surface.
It can form a group of beautiful sunspots with different polarities.
And very often it continues up into the chromosphere.
They rise higher up, and in the corona you can observe a coronal loop. And then in some of these cases you can form kind of evaporation, and then you form this cool plasma from below. It's kind of a cloud in the corona, and this forms a prominence.
And it also creates a variety of structures. All of them are linked, and the only way to understand them is to study the mechanism producing them, which is a magnetic field.
In addition to its light, the Sun extends the invisible threads of its magnetism from the interior out into the entire solar system.
There is strong connection. What happened in the deep part of the solar atmosphere, it goes through the whole atmosphere up to the interplanetary matter.
The magnetic field is not only the origin of all the phenomena we observe on the Sun, it is also responsible for its cyclic behavior.
Over the 11 years, roughly, of a solar cycle, everything changes on the Sun. When I'm at minimum, I see no sunspots, there are basically no flares, no activity. The Sun is very bland when seen in white light. When I go to maximum, it's full of spots. The corona is very bright, very extended. I have flares, coronal mass ejections, etc. So it's a totally different Sun at these two times. At the same time also, the magnetic field of the Sun is totally different at the two times. So it is these changes in the magnetic field which are actually causing all the changes in the cycle.
The global dynamo is responsible for the solar cycle.
However, there is a lot of controversy how this dynamo actually works.
And this is not the only controversy. In fact, to understand the Sun is to understand its magnetic field.
How does solar magnetism work?
How the magnetic energy is transported.
How sunspots are formed, how they decay.
Why the Sun has a cycle of 11 years?
How is the magnetic field produced?
And heat the plasma and accelerate the plasma.
There is a lot still to discover about the Sun because it's such a complex system.
The telescope opened up a torrent of questions. To find their answers also depends on this instrument.
We are taking telescopes and we are looking at the sun with those.
Trying to understand everything related to magnetic phenomena on the solar atmosphere.
But one thing we have found out, what is always holding us back, is that we can never resolve the small structures where the action is really happening, where the physics is, the basic physics is taking place.
The European Solar Telescope is a pan-European effort to build a 4-metre solar telescope. An extraordinary machine to measure the solar magnetic field like never before.
Magnetic field resolution sensitivity is more like 100 Gauss. You can do better if you have a larger telescope, if you can accumulate more signal.
So more precise measurements of plasma motions or magnetic fields on the sun you can do.
We expect to start approaching the scales where this interaction between the magnetic field and the plasma takes place.
But having a large telescope is not enough. With every observation, solar astronomers have an enemy to confront: the Earth's own atmosphere, the seeing.
The seeing is something that really influences the observations. What we need is clear air with just a little bit of wind, not too much wind, because what is called seeing completely blurs the image.
The turbulence in the Earth's atmosphere changes at very fast scales, milliseconds.
So we need to have very sharp images, and this happens only during exceptional moments at exceptional sites.
The Pygmalion Observatory was built in 1878. People realized that it is a very good site for observations because the sky is very clear and also the atmosphere is very stable. Professor Jean Roche designed a specific dome which is completely closed in order to avoid that the warm air from inside flows up through the aperture of the window in conventional telescopes, which degrades the images.
Thanks to this technology, at Pic du Midi Observatory, it was possible to see intense magnetic fields also outside of sunspots and active regions. The bright points.
The bright points are very teeny bright features located in intergranular lanes.
These are positions where the magnetic field is very intense, but they are very small. They measure about 100 kilometers in diameter.
And they interact with granulation.
They are very dynamical, and we use them to trace the evolution of the magnetic field in the solar atmosphere.
Making observations at the Pic du Midi Observatory is quite not so easy, especially in winter, because the winter conditions are very hard, especially temperature conditions which may reach 15 degrees below zero.
We need to observe the sun literally from above the clouds. And in Europe, that site had a name: the Canary Islands.
When I came to the Canary Islands, and at that time we were actually observing only with a 50 centimeter vacuum Newton telescope, and I looked at the solar surface structure at solar granulation, at sunspots, and saw them with my naked eyes, and it took my breath away.
The consortium behind EST is clearly inclined to construct EST here in the Canary Islands.
The Canary Islands are probably the best location that we have at our disposal within Europe for looking at the sun and at the stars in general.
Geography of the mountain sticking up very steeply from the cloud layer, that it would be a very good site for a solar telescope.
And that is why the most important European large solar facilities are installed here.
At Teide Observatory in Tenerife and at Roque de los Muchachos Observatory in La Palma, sit the most important solar telescopes currently in operation. They are fundamental to our understanding of the Sun.
Today, the main observations that are done in VTT is measuring the solar magnetic field and velocity.
One of the most productive solar telescopes in the 2000s.
The SST is in some ways a perfect telescope, you might say, because it is very simple in terms of optical design. It is very high optical quality. This allows us to measure the temperature, the gas velocity and the magnetic field at many heights in the solar atmosphere.
The special thing about Gregor is that it's an open telescope. We can completely fold the dome open. We can analyze different parts of the Sun with different instruments. So right now it's the biggest European solar telescope, and the unique thing is really this open construction, which is also now favored for EST.
All these facilities in some years from now, they will be outdated in the sense that we will have extracted the best from them, and we need a more powerful telescope to observe the Sun. This can only be accomplished with a joint European effort to design it and to build it.
At the top of vast white towers, solar telescopes rise several tens of meters above the ground. Why? To be closer to the Sun?
Yeah, solar telescopes have one problem. You observe during the day, so the Sun is heating the ground, you have turbulence.
And the solar observations require a telescope which is as high as possible to avoid this turbulence.
With the imaging optic mirror system, like a coelostat at the top of it, which just redirects the sunlight into that telescope.
And then we go downstairs into the lab where we have all the instruments.
So it is an easy way to build a relatively large and complicated instrument with very few moving parts.
EST will be constructed on a 44-meter high tower, but the immense heat will continue to be a big problem. Can you imagine standing under the Sun for hours with a huge magnifying glass over your head?
The main difference between the normal, the night telescopes and solar telescopes is due to the heavy heat load coming from the solar radiation.
With about 2 kilowatts of optical power which arrives at the primary focus.
And that's about the heat of a cooking plate. And when you have so much heat, it is very difficult to avoid that something gets warmed up.
So the movement of turbulent air inside the telescope, the instrument can destroy the image quality. For EST, we decide to move toward heat rejector, and then we want to reduce the amount of radiation coming from the Sun and rejecting the radiation outside.
The need for sharp images has led to the development of adaptive optics, optical systems that are literally alive.
Adaptive optics is a system of active optics, constantly updating.
So the movement of the mirror correct the modification of the radiation coming from the Sun to keep the quality of the images.
And they correct for the variation of the seeing in real time.
Is a technique without which no modern solar telescope could operate.
The concept of adaptive optics is now being taken a step further. The goal? To observe the Sun as if there were no atmosphere. This is one of the main technological challenges for EST.
With EST, at least, we have the idea to develop the most powerful adaptive optics system for any existing telescope, and we still need to demonstrate that this is a feasible system, working system.
The first solar observers put up their rudimentary telescopes in gardens and on rooftops. They carefully describe their observations in logbooks. But what does a day in the life of a professional solar astronomer look like today?
A solar physicist in an observatory sits in a room that sun can never shine. If you have a small hole or window, you get a contamination.
When we are here, we usually work 12 hours per day, but we have something new every day.
You look at a very complex source. You design and develop fantastic instruments which can answer your questions. You work with a lot of fantastic people, and you can sleep at night.
However, on the night of September the 1st, 1859, the English astronomer Richard Carrington probably did not sleep well. That morning, he had witnessed something very unusual on the sun. Two intense beams of light appeared next to the group of sunspots he was drawing. Strong auroras were seen around the world, in far-flung places such as Cuba, China, Greenland, and France. Telegraph systems failed in Europe and North America, and magnetometers on Earth detected an extraordinary geomagnetic storm. The Carrington event was one of the most intense solar storms ever recorded. But this was not an unusual event for our star. Quite the opposite.
The sun displays a whole range of explosive and eruptive phenomena.
For example, there are flares, which have energies of millions of atomic bombs, and they happen on average once per month, the big ones.
The other main class of large eruptive phenomena are the coronal mass ejections. Billions of tons of hot coronal gas, this is gas at millions of degrees, being thrown out into interplanetary space at speeds up to 2,000 kilometers per second.
This energy and this mass can go to the Earth.
And then we see northern lights on Earth.
Thanks to the Earth's protective magnetic field, auroras are the most evident and harmless effects of explosive solar activity. But sometimes, they are not the only ones.
We have many more delicate electronic instruments in places where they can get damaged by these very energetic charged particles coming from the sun.
Mobile phones, we have GPS, we have everything like that, satellites. So if the sun decides just to produce a big flare, everything will be switched off.
So, on the one hand, the sun, very important, very positive, absolutely necessary for life. But on the other hand, it also has negative effects.
There is a concept that describes the sun's complex influence on its environment, including our planet: space weather.
Space weather is a new science which developed recently, since 10 years, I would say.
Space weather is very important because in this advanced technological civilization, it can shut down your expensive satellite. It can change your navigation of commercial flights.
The Stone Age people didn't care whether the sun produces a flare or not. We do.
Predicting exactly when a solar storm will occur is crucial to anticipating its effects. But to do this, we must first understand the origin of solar activity in detail.
Solar activity, in general, is governed by the solar magnetic field.
Flares happen when the solar magnetic field gets twisted and then relaxes into a better state, an energetically favorable state. This relaxation is called reconnection, and it happens very fast, probably less than seconds, and it accelerates particles.
At the moment, it's not possible to predict reliably when a flare will occur or a coronal mass ejection will erupt.
Space weather today is like weather prediction 50 years ago.
So, what do we need to forecast space weather like we do today for the weather on Earth?
In future, to be able to predict those flares, we need to understand the physics.
How magnetic field interplays with plasma.
And to be able to understand this physics, we have to resolve and to observe those details.
EST will help to understand what magnetic topology at large and small scale will be needed to produce a flare.
But even features on the Sun move with high velocities, sometimes up to 100 kilometers per second. So if you want to track these features, your observations have to happen fast, within seconds or even fractions thereof.
Particular strength of the European telescope will be its temporal resolution. And it means that we will be able to detect very fast processes, like, for example, solar flares.
Perhaps someday we will be able to predict the Sun's behaviour in detail. But until then, we can only observe and monitor our star daily, as we have been doing for 4 centuries. It's essential for our society. We need dedicated solar patrols.
But we need the capability to look at the Sun 24 hours per day, 7 days per week, in order to understand the Sun as the complete, full physical system.
At the Lomnitsky Peak, we performed patrol observations from the beginning, from 1967, and it is primary focus to observe the corona.
Because the solar corona is a place where everything what comes to Earth must go through.
If you want to observe corona, then you need a really very special telescope, which is different from even from the typical solar telescopes, because you need to block all the light coming from the Sun.
The special instrument is called coronagraph. Eclipse in-house.
The solar corona, the Sun's very faint extended envelope, where one of the most persistent enigmas of solar physics occurs: coronal heating.
The one which we are still not able to answer is why corona is so hot.
How can it be heated? Because the heater is far away, that's in the interior of the Sun. And as we move out, suddenly it gets very hot.
EST will be designed and optimized for some observations. It will provide amazing spectropolarimetric observations of chromosphere, for example, and photosphere, but it will not have possibility to observe corona.
And then we combine that observations with our observation of the corona.
However, there is really only one way to observe the Sun continuously, including the corona: in its natural environment, in space.
On the other hand, there will also be space missions like Solar Orbiter.
Solar Orbiter is a mission of the European Space Agency and NASA to measure the magnetic field from a different direction than you see from the Earth, by going out of the ecliptic to make a detailed map of the magnetic field at the poles and how it changes over the solar cycle.
In general, space missions have the advantage that they can observe in the ultraviolet and X-rays with wavelengths that are not accessible from the ground.
Which are coming from the corona of the Sun, the hot outer layer. So that's the only way of seeing the corona all the time on the disk of the Sun, in front of the Sun itself.
Observing the corona from space, like Solar Orbiter, and the deeper layers with EST will give us a complete view of the coupling of the solar atmosphere by the magnetic field.
There's strength in numbers.
EST, these endosatellites.
Sunspots, flares, solar ejections. These are the most evident manifestations of the formation of intense magnetic fields on the Sun, the so-called active regions. But what happens on the rest of the solar surface, or in quiet periods when the Sun is a spotless white disk in the sky? Does the Sun lose its magnetism? No. We now know that magnetic fields are always present, even in the most quiet areas, even during the Sun's least active periods.
The magnetic field in the Sun, in the quiet Sun, is a quite recent discovery, because when we talk about the Sun, active Sun, we refer to active regions, so sunspot, facula mainly. But when we start to observe the Sun with the new instruments and we zoom into the photosphere, we are able to observe a very small intermittent magnetic field.
We didn't expect those tiny magnetic fields. The strongest ones give rise to magnetic bright points, and they are organized in a reticular pattern called the magnetic network. These are cells that extend over the solar surface, and they contain also a lot of magnetic fields, but extremely weak field.
But these weak fields store an immense amount of magnetic energy at spatial scales we still cannot reach, even with our most advanced telescopes.
In the quiet Sun, people thought for years that there is nothing. But we know that there is magnetic field everywhere, no matter where we look. And so far we cannot resolve it even. We don't see the smallest spatial scales of the magnetic fields.
The magnetic total budget of the Sun is dominated by quiet magnetic field. To study the magnetic behavior, the global magnetic behavior of the Sun, we need also to study the very small scale magnetic field.
The European Solar Telescope is necessary because it provides a unique capability to study very enigmatic and very tiny magnetic elements on the solar surface, which we believe to be essential for the generation of magnetic field in the Sun as a whole.
For the first time, I think we will be able then to see the fundamental building blocks of solar magnetic fields.
This weak and ubiquitous magnetic field may hold the key to understanding many processes occurring in our star. Coronal heating, the Sun's violent eruptions, or even the nature of the space weather that influences the entire solar system. But how does something small and ubiquitous connect with the big and explosive? The answer may lie in the thin layer between the photosphere and the corona, the chromosphere.
When you go up into the higher layers, into the chromosphere, this magnetic field expands and fills the whole volume. So in the chromosphere there is magnetic field everywhere.
This is the link between what is happening below the atmosphere and what is happening in the corona with this fantastic mass and energy releases. And everything is happening in a very thin layer of a couple of thousand kilometers.
When we look at magnetic fields in the chromosphere, they are very weak and very difficult to measure.
IST will play a fundamental role to study these weak signals and to understand how they contribute to this transport of magnetic energy.
Because it will be able to observe the Sun with different instruments that observe the Sun at different layers simultaneously.
To understand and connect all aspects of the Sun's behavior, from its interior to the limits of the solar system, this is the great challenge for solar physics. This is the prime objective of the European Solar Telescope.
But now we have a very good chance to do it.
Sunset at a solar observatory. Our protagonist hides below the horizon. Taking its place, countless new suns appear, shining from an incredible distance.
So most of the stars that we observe in the universe are very similar to the Sun.
And if you look at all the stars in the sky, you only see point sources.
Sun is our nearest star. It's the only star where we can see surface details, where we can resolve things.
So understanding the Sun leads us to the understanding of the other stars.
And this means that we can know better the universe by knowing better the sun.
More than 400 years have passed, but we will still feel the same emotion and curiosity that made Galileo point his telescope at the sun.
I think I can sympathize with Galilei, who has first looked at the sun and discovered unexpected things. But I think today we are still looking with the same kind of amazement, because there are still so many effects and phenomena that we cannot understand.
Hydrogen, helium, gravity, and a pinch of elements produce a complex system that actually we are not able to understand completely. In fact, we need EST for this reason.
I don't think we can overestimate how strongly a large telescope like the European Solar Telescope will change what we know about the sun.
EST for sure brings a lot of new questions rather than answers.
Devil is in details. So when you go in more detail, more questions will arise.
And that's what makes it so exciting. There is always a new horizon to go to.
This is the simple story of science.
So for sure, EST will make possible the detection of new phenomena that we cannot think at this moment.
The European Solar Telescope represents the next major step in our attempt to understand the source of life on Earth. 4 centuries into the future, we will still be reaching for the sun.
The woman who became my wife when I was traveling between La Palma and Sweden. Enormous impact on my life as well.
Our life is dominated by the sun.
The sun is the most important thing in my life at the moment.
I have spent more than half of my life studying solar physics.
And I think I could spend another few lifetimes studying it.
So the sun is the only star where we can actually see intricate detail.
Light is exception in the universe and dark is the nature. So to bring us the light, it is amazing.
And understanding why, it's the most fascinating thing about the sun.
And that is up to today a very challenging thing to do.
This is not an easy task, but when you get there, it's really exciting.
So it is not so easy, but it is also interesting. We have to fight with the weather.
Never get bored by observing the sun.
I have the same opinion.
Every time you go to the telescope and observe the sun, it's like the first time you see the sun.
My favorite thing about my job is that no 2 days are the same.
For example, a day you have a documentary team.
Exactly.